Hello everyone, my name is Taimeng Fu. I'm a year 2 undergraduate student from the Chinese University of Hong Kong, Shenzhen. The topic I have been focused in this is the automatic multimodal calibration of stereo cameras, thermal cameras, and lasers in arbitrary senses. My mentors are Dr. Huaiyu, Dr. Yaoyu Hou, and Professor Sebastian Schiller. Thanks for their guidance in this program. The research motivation is that today's robots are usually equipped with different kinds of sensors to better perceive the environment. To combine use data from those different sensors, we need the precise extrinsic calibration between them. Traditional calibration methods are only designed for sensors in no more than 2 modalities, and most of them either require specific calibration targets or manual manipulation. So it's inconvenient to use them, especially as the sensor type increases. So here, we introduce our automatic cross-modal calibration framework for stereo cameras, thermal cameras, and LiDAR sensors. It has several advantages. First, it performs the calibration automatically, and it can work in arbitrary senses without any specific calibration target. And it calibrates the stereo cameras, thermal cameras, and lasers in one system. The key insight of the algorithm is to extract edge information from the data of different sensors and align those edges by minimizing the registration error on extrinsic parameters. The flowchart of our pipeline is shown below. It has 3 major parts: the stereo point cloud generation, stereo laser calibration, and thermal extrinsic calibration. For the stereo point cloud generation, we first extract image features by SIFT, match those features between stereo pairs, as shown below in the left, and triangulate on those matched features to get the stereo point clouds, as shown in the right. Then we do the stereo laser calibration. We use the Generalized-ICP algorithm to register the stereo and laser point clouds. GICP is a variant of the ICP program. It optimizes not only the point-to-point, but also the point-to-line and point-to-plane distance. The registration result is here, where the white points are the stereo points and the blue ones are the laser points. The next step is the thermal extrinsic calibration. We first extract edge information from the data of those 3 sensors, and we project the edge points in the stereo and laser point clouds onto the thermal edge maps by an initial guess of the extrinsic. Then optimize the extrinsic to minimize the reprojection edge alignment error, which is shown below. So here is a comparison about before and after the calibration. So the background images are the thermal images, and the red points are the reprojected stereo and laser edge points. We can see that the calibrated transformation gives a more accurate projection edge alignment, which indicates an accurate calibration result. In conclusion, we contributed a multimodal calibration pipeline for stereo cameras, thermal cameras, and lasers. The pipeline greatly reduced the complexity of the calibration process, since the user only need to provide it a rough initial guess of the transformation and the synchronized data frames. And it gives pixel-level aligned extrinsic calibration results, which can be used in higher-level tasks, such as 3D reconstruction, dynamic visual odometry, and so on. So that's all. Thank you for listening.